I've decided to redo this video because I found some problems with it, so I deleted the old one, which I put up a couple of days ago, and I'm redoing it here. To begin with, empty set E is not a set. For example, if A and B are sets, A is equal to B if and only if every member of A is a member of B and vice versa. That's the definition of set equality. Therefore, the empty set E is not a set because it doesn't satisfy the conditions of set equality. Very simply, it has no members, so it can't satisfy the condition. Now, I note, this has many broader implications and it's been discussed many times, but I do want to note here that a vacuous truth is ambiguous. It's either true or false, which means any proof dependent on a vacuous proof is ambiguous. It's either true or false. For example, if I have 1, 2, 3 is a subset of, I have 1, 2, 2 is a subset of 1, 2, 3 is unambiguous. E is a subset of 1, 2, 3 is ambiguous. It can be either true or false depending on depending on the vacuous, it's either true or false depending on the vacuous proof. Good, that's the way I want to put it. Now I'm going to discuss infinite or endless set I. Now I'm going to distinguish between two endless sets. One is I, is the set that contains C, and in this infinite set you can count to any member of I. Then I'm also going to have a set I contains W, where W has the property. There are members of I you can't count to. So I can pick a member of W and you can't count to it, 1, 2, etc. So now, if I is equal to C, that implies that Cantor's diagonal argument fails, and if it follows if you look at the argument and how it works. I'm not going to go through Cantor's diagonal argument. It should be pretty obvious. And if I is equal to W, which I will rewrite just because it's a little more obvious, if I rewrite it as CW, then Cantor's diagonal argument is superfluous. Therefore, I ask, does W exist? Since CDA is superfluous, I haven't proved that W exists, so I ask, does W exist? And the answer is yes. And why? Because Cantor says so. That's not quite as bad as it sounds. I mean, one can name abstract objects and build axioms around them and theorems around them. However, the problem is there's a language confusion between reality and abstraction. And that comes about because the only language available to build up your abstract system is real language. And unless you're careful, the only way to describe the results of a proof using your abstract system is you have to use the only words available to describe the results are real words, but if you don't make the distinctions, then you can get into trouble. For example, I is equal to the square root of -1. You can build a complex set of numbers using I which satisfy the axioms of a field and do all kinds of arithmetic with I. Where you can get into trouble, for example, is an engineer has a situation where there are a lot of possibilities to escape from it. But it's a very complicated situation. So he goes to a mathematician and says, look, I would like you to find out the possibilities for escape in this given situation. So the mathematician takes the situation, models it, works on it, and finally comes up with an answer and goes to the engineer and says, yes, the solution to your problem boils down to a cubic polynomial equal to 0. And he said, with mathematical certainty, that has 3 roots. However, if he doesn't say that 2 of the roots are complex, then the engineer is going to be in deep trouble. Right? Another example is the 4th dimension. In normal everyday language, 3 dimensions in normal everyday language, 3 dimensions is very clear. It's the position of anything as specified, say, by its x, y, and z coordinate. Now, when science comes along and says there is a 4th dimension without any clarification, then in ordinary language, I mean, that's woo, there's a 4th dimension. Are there other universes beyond our universe? However, if you clarify that the 4th dimension is time, then that's very clear and simple. You're saying that a chair which is at the position of x, y, z, you can also state that it's there at a particular time t. So it has a 4th dimension, the time when it was there. Another example is if you have a math theorem which utilizes an abstract result such that W exists, and then you couch the proof of the theorem in real language, it obscures the fact that buried in the proof was an abstract definition, namely W exists. So unless you specify that the theorem was based on an abstract definition, you can't just simply express it in real language. So what I'm saying is, to an engineer, the difference between real and language and abstract language is absolutely critical, because if he's not clear about it, then the results can be disastrous. Bridges can collapse, airplanes can drop out of the sky. I mean, if you're not carefully, if you don't make the clear distinction between abstraction and abstract language and real language, then systems collapse and people die. If it's a mathematical proof, well, and there's a problem with it, well, you can always write another paper. So finally, I would just like to comment on 0. If you want to count with a verb, you use the natural numbers 1, 2, 3. If you want to report the results of your count, in other words, count is an adjective, then you need 0, 1, 2, 3. And the natural numbers now, and the numbers that you use for count as an adjective are 0 and n. So here, 1, 2, 3 are the natural numbers n. So for example, if I have A, B, C, and I want to count them, if I want to count the members in this set, I count 1, 2, 3. I wouldn't count 0, 1, 2. I'm not going to get into more discussion of 0. It can get more abstract and involved. Thank you very much.